All right, now that we've talked about all of the individual pieces and components, we can bring them together looking at angular dynamics. So this works very similarly to linear dynamics. So in linear dynamics, remember we used sigma F equals ma plus the kinematics equations. Now we're going to use instead net torque equals I alpha plus the rotational kinematics equations. And this makes, the easiest way to look at this is just looking at an example. So let's jump into that. Consider a 12 kilogram motorcycle wheel as shown below. Assume it to be approximately an annular ring with an inner radius of 0.28 meters and an outer radius of 0.330 meters. The motorcycle is on its center stand so the wheel can spin freely. If the drive chain exerts a force of 2,200 newtons at a radius of 5 centimeters, what is the angular acceleration of the wheel? There's a lot of stuff said there, but you can kind of look at this diagram and we can kind of start taking it apart. But we see that we've got a force applied at a distance, so a force applied with a radius, which you see right here. That's going to produce a torque, and that torque is going to produce an angular acceleration of our wheel, right? This is going to cause it to spin because, right, you're kind of pulling here and it's fixed at the pivot here. So let's start working that. So torque, net torque is equal to I alpha, and we want to solve for alpha, so that means that alpha is equal to net torque, which is just the only torque that we have here, so I'm going to write torque divided by I, which in this case the torque is the force times the distance, and I, if we go back to the previous video, you can see that for an annular disk or annular cylinder or ring rotated about the cylinder axis, we have this equation here. So that's what we're going to use in a minute here, and I'll go back to it and I'll write it. And the equation is I equals 1/2 the mass times one of the radii squared plus the other radii squared. And again, you don't have to worry about how to get these. They'll just be given to you on the exam. So that means alpha is equal to the force, which is 2,200 newtons, times the distance of 0.05 meters, because we always need to be working in our SI units, divided by 1/2, and the mass we said was 12 kilograms, times the inner radius squared, which is 0.28 meters squared, plus 0.330 meters squared. There's a fair bit of algebra to do for that, and you'll get some answer that's going to be, what is this going to be about? This is 1/20th, so 1/20th of this is 110 Newton meters. On the bottom, that's going to be too close for me to do in my head, but you get something. You get the idea. You can plug it in your calculator and check. B, what's the tangential acceleration for a point on the outer edge of the tire? Well, we know that R alpha equals tangential acceleration or linear acceleration. So that means that A is just equal to the outer radius of 0.330 times the alpha that we get from above. And again, if you've got A, you can easily solve for B here. It should be an alpha. If you want me to go through this in class, you can pull it up and I'll be happy to. And then C, how long from rest does it take to reach an angular velocity of 80 radians per second? Well, we know that delta omega is equal to alpha delta t. This is just one of our kinematics equations. Delta v equals a delta t. And so this will equal omega minus omega naught is equal to alpha delta t. And so, in other words, delta t is equal to omega minus omega naught over alpha. We solve for alpha above. Omega naught is 0, and omega is equal to 80 radians per second. You can plug that in like before and get a delta t. So this is the idea behind angular dynamics. It's just the same things we did before, but there's some little tweaks because we're dealing with angular quantities. And so that will close out this topic, and there's only a few more to go, so you're almost there.